So this is our second topic under sequential circuits, the analysis and design procedure. Analysis describes what a given circuit will do under certain operating conditions. It is also to develop a complete design procedure for clock mode circuit. The behavior of a clock sequential circuit is determined from the inputs, the outputs, and the state of its latches or flip-flops. The outputs and the next state are both a function of the inputs and the present state. So the analysis of a sequential circuit consists of obtaining a table of a diagram for the time sequence of inputs, outputs, and the internal states. The logic diagram is recognized as a clock sequential circuit. It includes any flip-flop with a clock inputs. So we have this state equation. State equation is also known as a transition equation. It is an algebraic expression for your sequential circuit. This specifies the next state as a function of the present state and inputs. If we have to consider a sequential circuit with 2D latches, and it is labeled latch A and B with input X and an output Y. So this is our sequential circuit example with 2D latches, and the first latch is designated as latch A, then for the second D latch it is designated as B. The first we are going to do is to determine the state equation. It is an equation that will go to your input of your latches. So in your first D latch, we have to get the equation of this input. And for the second D latch, we have also to get the equation of this input. So for the first latch, we have an equation D, A, with an A is a subscript to determine that this is the first latch. So it is connected with an OR from two AND gate with one input of your first AND gate connected to A and the second input to your X. Whereas in your second AND gate, your second input is connected with B and X. So therefore, the equation of your first latch that is equivalent to EX or BX. For your second latch, it is connected with an AND with an input from E bar and X. So we have E bar X. A state equation is an algebraic expression that specifies the condition for the flip-flop or latch's state transition. The left side of the equation denotes the next state of the flip-flop one clock edge later. And the right side of the equation is the Boolean expression that specifies the present state and input condition that make the next states. Output equation is a Boolean expression of a present state value. So we have to determine your output, which is your Y, that is equivalent to your E or B, then it is AND with X bar. Next, we are going to get the state table. So from your state equation, which is dA, we have your dB and your output. So we have two columns to determine that is for your possible input combination. So we have for X, which is equivalent to 0 and X equivalent to 1. So first, if we have X equivalent to 0, so therefore all the X in your first column will become 0. And for X that is equivalent to 1. So all the X in your second column will become 1. And for your input A equals to 0. So at this time, we have now a value of your dB when you have an input A or your present state A equals to 0. So for the first column, when x equals to 0, so we have dB, which is 0 bar and 0, or that is 1 and 0. So therefore, dB at that time is equals to 0 when x equals to 0. And when x equivalent to 1, so we have dB, which is 0 bar 1, so that is equals to 1. Then for b equals to 0, so all the b must be changed with 0. So for your dA, when your x equals to 0, you have an output of dE which is equals to 0. And for your dE when x equivalent to 1, so we have 0 and 1, or 0 and 1, that is the same as 0. And for your y, when x equals to 0, it is 0, because we have 0 or 0, then and with 1, so therefore it is 0. When x equals to 1, so we have 0 or 0, then and with 1 bar, that is also the same as 0. The next, if your present state A is equals to 0, then you have your dB at your x equals to 0, that is 0. dB when x equals to 1 is 1. And your y when x equals to, uh, before getting your y, we have to solve first for your b. When b equals to 1, so your dA in your first column, or when x equals to 0, that is also 0. And for your x equals to 1, your dE is equals to 1. And for your y, we have for y equals to 0 or with 1, then and with 0 bar, that is equals to 1. On the other side, when x equals to 1, it is equals to 0 because you have 0 or 1, then and with 1 bar, so therefore it is 0. Then for your e equals to 1, when a equals to 1, we have your dB when x equals to 0 as 0, and dB when x equals to 1 is also 0. When your b is 0, dE when x equals to 0 is 0, when x equals to 1, it is equals to 1. And for y, we have when x equals to 0, we have y equals to 1. And if x equals to 1, we have y equals to 0. Then for a, for the present state A is 1. So we have dB, it is 0. And for x equals to 1, your dB is also 0. For b, which is equals to 1, for x equals to 0, your dE is 0. And for x equals to 1, your dE is 1. For your output, we have for x equals to 0, your y is 1. For x equals to 1, your y is 0. Then we have to rearrange this state table, where your x as an input, we have to put your x on the column together with your present state at the outer side. So we have your present state together with your x as input, then we have E and B, that is present state, then we have your next state and your output y. So this transition table or state table is the time sequence of inputs, outputs, and the state of the circuit. Then after you have your state table, we have to now draw your state diagram. So in your state diagram, first we have to determine how many states in your state table. So we have your present state variable, which is E and B. So therefore we have only 4 states because we have only 2 variables in your present state. So the first state is 0, 0. The second state is 0, 1. The third state is 1, 0. And the fourth state is 1, 1. Next, we are going to connect your next state when your input occur. So we have the first one, that is when we have 0, 0, when x equals to 0, it goes to 0, 0. So your x is 0 and your output is 0. Then another state, when it is 0, 0, it goes to 0, 1 when x equals to 1 and output equals to 0. Fourth state, 0, 1. The first is it goes to 0, 0 when your x is 0 and your y is 1. And the other one, it goes to 1, 1 when your x is 1 and your y is 0. For your state 1, 0, the first next state is it will go to 0, 0 if your x is 0 and your y is 1. And it goes to 1, 0 when your x is 1 and your y is 0. Then for the state 1, 1, the first one is will go to 0, 0 when your x is 0 and your y is 1. And it will go to 1, 0 when your x is 1 and your y is 0. So this is what you call your state diagram. So the information available in a state table can be represented graphically in the form of a state diagram. A state is represented by a circle and the clock triggered, that is, the transition between states, are indicated by directed lines or arcs connecting the circle. So we have this another equation. This time, it is a sequential circuit that uses JK flip-flop. So we have to determine the state equation of your first JK, which is designated as A, and also the second JK, which is designated as B. So for your first JK, we have to determine your G subscript A and key subscript A as input to your JK flip-flop. So your J is connected with B and your KA, it is connected with your X bar and your B. So we have B X bar. For your JK flip-flop B, so we have JB, which is connected to your X bar, and your key, it is connected from your A XOR X. Then we have to derive a state table as what we did in our previous slide. So you have to get your present state and the next state. So in this type of sequential circuit, there is no output given. So we have only the present state and the next state with your present state variable E and B and your next state variable also E and B with input X when X equals to 0 and X equals to 1. So this is now your state table. Then we have to arrange your state table that all your input together with your X and your present state must be on one column. So we have your present state on your input, then you have your next state. So remember, your input must be on the outer side of your column under your present state. After getting your state table, you have to draw your state diagram. So this is your state diagram. Now, you have this circuit. You have to do this by your own. From the sequential circuit, get the state equation, state table, state excitation table, and your state diagram. So how to design a sequential circuit? So the analysis process of the previous section followed a sequence of steps which successfully transformed the circuit's description. So in the design procedure, from the word description and specification of the desired operation, derive a state diagram for the circuit. After deriving a state diagram, we have to reduce the number of states if necessary. Then we have to assign binary values to the states, and we have to obtain the binary coded state table. Then you have to choose what type of flip-flops that we are going to use for your sequential circuit and derive the simplified flip-flop input equation and output equation. After that, using that Boolean algebra or your map method, then you have now your simplified equation, then you can do your logic diagram. So we have this example. We have to design a sequential circuit with input X and output Y. If your input X equals to 0, the sequence of your sequential circuit is from 0, 0, it goes to 0, 1, it goes to 1, 0, then 1, 1, then back to 0, 0. And if your X is equals to 1, your sequential circuit from 0, 0, it goes to 1, 1, then 1, 0, then 0, 1, then 0, 0. Output Y will become 1 if the number of 1 in the present state together with your input X is add. Then we have to use G key FF in the design. FF is the flip-flop. So we have this state diagram and state table. So we have to have your state table, which is your present state. Since we have 2 bits in your sequence, which is 0, 0, and the maximum is 1, 1. So we have to designate that one as A and B. Then for your column next state, so it depends on the input X when X equals to 0 and X equals to 1. As well as for your output, it will also based on your input X when X equals to 0 and X equals to 1. So we have your first state, which is 0, 0. It will go to 0, 1 if your X is 0. Then you have your input X equals to 0 and your output is equals to 0. Remember that your Y became 1 if the number of 1 in the present state together with your X is add. So your present state is 0, 0 and your X is 0, so therefore your Y is 0. Then if your X is equivalent to 1, so we have X equivalent to 1, from 0, 0, it goes to 1, 1. And your Y, since X equals to 1, therefore your Y is 1. For your next state, which is 0, 1, when X equals to 0, from 0, 1, it goes to 1, 0. So we have your X equals to 0, then we have to determine what will be your Y value. So we have input X, which is 0, and your present state is 0, 1, so therefore your Y is equals to 1. Then from that 0, 1, at X equals to 1, from that 0, 1, it goes to 0, 0. When your X equals to 1, then what is your output? So we have your X equals to 1 and your present state is 0, 1. So your number of 1 in your present state and your input x is even, so therefore it is 0 for your y. Then we have this state 1, 0. At x equals to 1, if we have 1, 0, it goes to 1, 1. So we have x equals to 0. Then how to determine your y? So we have to count the number of 1 including the input x. So it is add. So therefore your y equals to 1. Then when x equals to 1, from 1, 1, from 1, 0, that is 1, 0. From 1, 0, it goes to 0, 1. So we have your present state, which is 1, 0, and x equals to 1, so therefore your output is 0. Then for the state 1, 1, for x equals to 0, 1, 1, it goes to 0, 0. Then your y is equals to 1 because we have 3 number of 1s in your present state as well as your x. That is 1, 1 when x, that is 0, by the way, 0 because your x is 0. So we have an even value of your number of 1 in your present state as well as your x. Then when x equals to 1, from 1, 1, it goes to 1, 0. This time, we have to count the number of 1. Your present state have 2, 1, and your input x, which is 1. So therefore, you have an add number of 1 in your present state as together with your input x. So we have 1 as your output. Then we have to arrange this state table where your x is part of now of your present state. Then you have your next state and your output y. After arranging your state table, so we have to create your excitation table. Excitation table, that is where you have your flip-flop incorporated to your table. So we have the present state when x equals to 0 and 1, and we have already your output. Then we have to determine what will be your input combination of your flip-flop if your present state going to your next state. So we begin with your present state A, then going to your next state A. So as you can see in your state table, present state E is 0, it goes to 0 as your next state. So from 0 going to 0, that is 0x. Then for your B, it is 0, it goes to 1, so that is 1, 0 at your GBKB. Then next, we have 0 to 1, so that is 1, 0 at your GAKA. That is 1, 0, that is 1x. So that is 1x. Then we have 1 going to 0 for your B, so that is equivalent to x1. Then next, we have 1 to 1, so it is equivalent to x0. Then we have 0 to 1, it is equivalent to 1x. Next, we have 1, 0, it is equivalent to x1. And 0, 1, 0, another x1. 0 to 1, it is 1x. 0 to 1, it is 1x. 0 to 0, it is equivalent to 0x. 1 to 0, that is equivalent to x1. 1 to 0, it is x1. 0, 1, 1x. 1 to 1, that is equivalent to x0. Then 1 to 0, that is x1. After that, using your map method, we have to determine the equation of your JA, KA, JB, and KB. So that is what you call your state equation. So using map method, solving for your JA, since we have only 3 variables in your input, so we have 8 square for your maps. So we are using your 3 variable map. So for your GA, we have 0, 1, XX, then 1, 0, XX. So we can group this by 2 and by 2. So we have the first two, that is X bar, B, and the second two, by rolling the map, we have X, B bar. So therefore, that is X, X, or B. For your KA, we have X, X, 0, 1, X, X, 1, 0. So group this by 2 and another by 2. So KA, that is X, X, or B. Then for your GB, we have 1X, 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 1X. Group this by 4. So your GB is equals to 1. For your KB, we have X1, 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 X1. So we have to group this by 8. Then KB is 1. For your Y, so we have 0, 1, then 0, 1, 0, 1, 1, 0, then 0, 1, and 1, 0. No, 0, 1, 1, 0, then 1, 0, 0, 1. Okay, so we have to group this by individual 1 with a common of X bar and X for the first row and the second row. So therefore, we have X bar, A, X, or B, or X, E, X, nor B. Or we can rewrite that one as X, X, or E, X, or B. Then we have to draw your sequential circuits. So this is now your sequential circuit. Another is we have to design a combinational circuit with X and Y as input. If X, Y is 0, 0, the circuit sequence are as follows: 0 to negative 4 to 6, then back to 0. If your X, Y is 0, 1, it is from 1, 3, then goes to 5, goes to 7, and then 1. If it is 1, 0, you have 0, 1, 2, 3, 4, 5, 6, 7, then back to 0. If it is 1, 1, that is 7, 6, 5, 4, 3, 2, 1, then 7. Then you have to use JK and gates. You have to show your state table, state diagram, as well as your excitation table. And you have to draw the circuit. So the maximum value of your sequence is 7. If you have to change that into binary, so that is 1, 1, 1. So it means that you will be using 3 JK, and you have to designate that one as A, B, and C. So you have to do that and pass that on the next meeting.